Hey there, and welcome. Have you ever stood at the base of a massive skyscraper, looked all the way up, and just thought, how on earth is that thing still standing? Well, it's not magic, not by a long shot. It's a set of rules, an unseen blueprint that's been carefully perfected for decades. Today, we're going to pull back the curtain on that very rulebook. I mean, really, think about that for a second. We're talking millions upon millions of pounds of steel, glass, and concrete, all soaring into the sky. What is the fundamental secret, the core knowledge that ensures it won't just topple over? The answer lies in one single, incredibly powerful document. So here's our roadmap for today. First, we're going to uncover this unseen rulebook. Then, we'll get into the raw ingredients and the powerful forces they're up against. We'll see how it all gets joined together, follow a piece of steel from the factory to the skyline, and finally, we'll understand why this whole thing is really built on a foundation of trust. All right, so let's start with the book itself. You can think of it as the master instructions, the one manual that every single engineer turns to when they're designing with steel. And the keepers of this master plan are the American Institute of Steel Construction, or the AISC. This isn't just one person, it's a committee of the best of the best. You've got the academics doing the research, the engineers designing the actual buildings, and the fabricators who physically build them. All of them working together, constantly updating and refining these rules to keep us safe. And this is their masterpiece, the Specification for Structural Steel Buildings. The best way to think about it is as the official cookbook for engineers. The whole point is to create a uniform practice. That means an engineer in New York and an engineer in Los Angeles are using the exact same time-tested recipe. That's how you get predictable, reliable, safe. Okay, so if this thing is a cookbook, what are the ingredients? Well, that brings us right to our next section, the raw materials and the unbelievable forces they have to stand up to day in and day out. Of course, it all starts with the steel. But listen, you can't just use any old steel. The specification is incredibly strict about this. It only allows steel grades that meet very specific standards from ASTM. That's the group that basically sets the quality benchmark. It ensures every single beam has a known, verifiable strength. You have to start with top quality ingredients, no exceptions. So, once you've got your steel, you have to figure out what you're fighting against. The specification boils it down to four big forces. First, there's the dead load. That's just the building's own colossal weight. Then you've got the live load. That's us, our furniture, snow on the roof, you name it. And then come the heavy hitters, the immense force of the wind, and of course, the violent shaking of a potential seismic event or an earthquake. But here's the really clever part. A building doesn't just face one of these at a time. So the specification forces engineers to design for load combinations. They have to imagine the absolute worst-case scenario. Like, what if a hurricane force wind hits the building on a day when it's completely full of people and equipment? They have to design for that perfect storm to make sure the building will always be ready. So we have our high-quality steel, and we know what forces it needs to resist. But a single beam doesn't do much on its own. It has to connect to everything else. And that brings us to what is easily one of the most complex and critical parts of the entire rulebook, joining it all together. Honestly, you can think of a massive skyscraper as just a giant kit of parts. The real magic, the thing that makes it all work, is in how those parts connect to each other. Chapter J of the specification, the chapter on connections, is one of the longest, for a very good reason. This is where the building's true strength is born. Now, when it comes to connecting steel, you've really got two main tools, welding and bolting. Welding is literally melting the steel together to make one solid piece. But the rulebook is clear. You have to control the heat and the sequence perfectly, or you'll warp the steel. Then there's bolting, where you use these incredible high-strength bolts to clamp steel together. And the key rule there? Each bolt has to be tightened to a specific and absolutely enormous tension. And this drawing right here shows you the level of detail we're talking about. Nothing you see here is random. The number of bolts, how far apart they are, the distance from the bolt to the edge of the steel plate, every single one of those dimensions is precisely calculated using formulas from the specification. The whole goal is to make sure the connection is even stronger than the beams it's holding. And to give you a sense of the insane forces at play here, get this. A single standard high-strength bolt has to be tightened so much that it creates a clamping force of over 70,000 pounds. That is the equivalent of parking 3 elephants on top of one little bolt. And a big connection might have 100 of them. So why all these hyper-specific, nitpicky rules about spacing and distances? Well, because of this. This is a diagram of something called a block shear failure, where an entire chunk of steel literally rips out of the connection. This is exactly what those detailed rules are designed to prevent. Every rule is there because someone somewhere learned a hard lesson. Okay, so the engineer has done the math, the connections are designed. How does all this turn from a blueprint into an actual building? Well, now we follow the steel as it leaves the design phase and enters the real world, from the shop floor to the job site. Chapter M of the specification lays out this whole journey. It starts with shop drawings, super detailed instructions that tell the steel fabricator exactly how to make each piece. Then comes fabrication, where they cut, drill, and shape the steel in a controlled shop. After that, it's erection, as cranes lift each piece into place. And watching over the whole dance, quality control. And the rules here are incredibly practical. For instance, the spec says that if you're using a torch to cut thick steel, you have to preheat it to 150 degrees first, just to prevent tiny invisible cracks. It demands that the frame is temporarily braced during construction, so it doesn't get blown over before it's finished. Every little detail is covered. And here's the key. This is not an honor system. The rulebook mandates that the entire process, from the moment the steel is made to the second the final bolt is tightened, is subject to constant, rigorous inspection. It's the ultimate check, making sure the building in the real world is a perfect match for the one on the blueprint. Which brings us to our final thought. When you step back from all the formulas and the temperatures and the bolt tensions, you start to realize that this document is so much more than just a technical manual. This quote right from the specification's own preface really says it all. The goal is to make safe design routine, to create a uniform practice. It's about taking something mind-bogglingly complex and making it dependably, boringly safe every single time. It's about making excellence the everyday standard. And that, right there, is the real heart of it. This rulebook is basically a social contract written in steel. It's the collected wisdom from generations of engineers, all poured into one place. It creates a system of trust so powerful that you and I can walk into a 100-story skyscraper and not even think twice about it. We just know it's safe. It really makes you wonder, doesn't it? From the software that runs our banking system to the safety protocols for air travel, what other invisible rulebooks are out there quietly holding our modern world together every single day? Something to think about.